All right, line I1, learning test 3, we're going to talk about the testing of protective devices. Now, the whole point of us using circuit breakers and fuses is the fact that they are designed to go and open up, right? That's the thing, is that they're supposed to, if there's too much current, they're supposed to go and shut something down. So what we're usually looking for with them is going to be an open in a circuit. The problem is that it is not always going to go and be visible. For a circuit breaker, yeah, we sometimes will see the little flag in the window that'll pop up, or the handle will have moved to the central position, or there's usually some other type of visual indication that we have got a tripped breaker. For fuses, we don't usually have that. There are some fuses out there that will have a little visual indicator window that will show us when there is something that has happened with that fuse. But the bulk of them won't do that. So usually everything is going to be found through the use of an electrical meter. Couple of different ways that you can go about doing this. One of the methods that they have is going to be detailed inside of here. Now, I do want to point out that this method is a good method. It's a useful method. However, it's not always going to be your first method that you are going to go to. If I can remove the fuses, rather than doing this whole crisscross, fuse testing thing, in a lot of cases, if my fuses are small, we're talking like 60 amps and under, I'll just pop the 3 fuses out with a set of proper fuse pullers, because I have some, you should have some too, and then I will just test those fuses individually, one by one, and then you find out which one is bad, if any, and then you're going to go and put them back in. Where this type of methodology works really well is when you're looking at some of those bigger fuses. Go back to your learning task 1, take a look at those L type of fuses. Once you get up into a couple thousand amps, there's a lot of bolts to undo in order to go and open up, or to go and remove one of these fuses from there. So we don't want to necessarily remove every fuse out of there. If it's easy, we absolutely will usually go and remove them and just test them. You verify them like that with your meter, and then put back in good ones, replace anything that has blown up. The thing to be aware of when testing fuses as well is just how you are testing them. If you are going to remove a fuse and test the fuse for continuity, that's the most common way that we're going to do that, is we're going to go and have a fuse, and then we will test that thing for continuity, right? Here's my general cartridge fuse over here. Be very careful how you test it. I have watched apprentices take their voltmeter, take out a fuse, and then they are going to go and take their voltmeter, they'll change it to ohms because they're going to look for continuity, and then they're going to go measure across here, and they're going to go measure across here, and they're going to say, yep, that fuse looks good, and they'll check all 3 fuses, and they'll put them back in, and I'm just going to stand there and shake my head because I just watched them take that fuse out of the fuse holder, lay it in the bottom of the metal can, and then test by placing their probes across it. If you are going to test a fuse by, taking it out, make sure it is not lying on top of something that is already going to be conductive. What happened in that situation was that apprentice was merely testing the continuity of the can to read from ferrule to ferrule. That's the caps on the end of the fuses. So don't, lay them on top of something metal and then test them, because you're not going to get the correct one. All right, let's talk about in-situation testing, though, for when these things are actually still in line. Start with a visual inspection. Sometimes you will see actual rupturing that's going to happen on the fuse. That's pretty obvious. Something's happening. If it's ruptured, it's probably also fairly dramatic, meaning that we've seen a short circuit or something like that. Sometimes we will also go and see evidence of heat. It could be discolored components. Copper will get kind of this reddish, dark sort of color. We can see insulation that's maybe a little bit, distorted or something like that. We can also sometimes see, on the wires themselves, that they're just sitting a little bit loose inside of there. Anything like that is going to go and introduce heat and can cause nuisance tripping, right? We don't want to see any sort of nuisance tripping. When you're opening up a panel to put new stuff in, while you have the power off to put those new breakers in, you should also be checking all your connections, right? They loosen off over time. All right, going into our analysis over here, what they're showing us is a 3-phase motor. And it's a 3-phase motor that's got a number of components that we maybe have not covered yet in depth for some of your apprenticeship. This section over here, these 2 boxes, are going to go and be what we refer to as a contactor and overloads. We will do some motor control later this year. We'll talk about those things later on. Overloads over here are simply heaters that are going to go and generate heat, and that if that heat would get too much, they're going to go and trip out the circuit breaker itself. or trip out the contactor, which is switching the circuit itself. That's going to go and protect the motor windings just in case we got too much current going through them. Upstream of that, we're usually going to go and have this that is all going to be inside of a single disconnect switch. We call it a fusible disconnect switch because we're able to go and place fuses inside of those carriers. If we are going to be testing, a couple of different methodologies for testing. One is going to be live testing, checking for incoming power. The other one is going to be dead testing. Now, I'm going to once again take a look at this thing separate from the way that the binder lays it out. The binder lays it out as if we always need to be testing with all the power on. We don't need to be testing with all the power on. Can we do continuity checks with voltage? Absolutely not. We cannot ever be checking the ohms if we have got the circuit powered up. But if we don't, if there's an incomplete path for a current flow, we absolutely can. So if this is my disconnect switch, what I can do is, if these are my incoming lines over here, I can just throw the disconnect switch. So these three are going to be tied together to my actual handle. Throw the disconnect switch. When I do that, I can safely take my ohm meter and I can, without removing those fuses, just measure across from top to top, top to top. Do note that you could only do this if the switch itself were open. So I could measure this fuse, measure this fuse, measure this fuse. There's no complete path outside of what I'm looking for. If that fuse is blown on the inside over there, you see that this side over here is completely isolated. We would obviously have no continuity. At times, we will have to go and do live testing to go and verify components. You know, you might not know what is dead or why you've got a section of your installation that's not working. So in those cases, you will actually have to check stuff on your fuses. Remember that a fuse is designed to open, but it's also designed to act as a conductor until it opens, which means that really, whatever I see for my voltage from here to here, I should see as my voltage from here to here. Right? It's acting as a conductor unless it's going to go and open. So what I will do is I will first start by measuring across the tops of all my fuses. Check that I've got proper line voltage, 1 to 2, 230 volts. This is a three-phase system once again. So we get line voltage from all three lines across to each other. You know, the next one over here, line to line, check. Next one over here, line to line, check over here. The next thing that I'm going to do is I'm going to go and use what's called the crisscross method. The crisscross method is nothing special. All that the crisscross method does is it says, hey, does my voltage change if I take this lead over here and I slide it over top of this fuse? Because this fuse is just a conductor, right? If the fuse is good, it should be the same. That's what we're seeing inside of the crisscross method, is that the electrician started by having the leads across there, and then they just slid this one down and across the other side, and they're verifying. Do I still have the same value of voltage? You know, okay, then that fuse, the one that I'm on the low side, must be good. Then they move across, keep this one on top of here. They start up here. They had 230 volts on that one before. Remember, we saw that right over here. And then they slide that thing down, and all of a sudden they're seeing a 0 volt or an oddball voltage. It would really depend on what's connected downstream. Sometimes it will be 0. Other times, it will be just an odd voltage, depending upon what the impedances are in the system and the three-phase balancing and a whole pile of other components. Okay, so I'm going to verify, yep, that thing's got 0 volts. What I'll then do is I'll say, well, I just checked off of that one. What I'll then do is I'll move over to the next one over here. I'll move my, what we refer to as my reference lead. I know that before, when I had a reference lead on there, and this lead over here, I measured 230 volts. I'm now going to go and try and replicate that, but I'm going to move that one once again to the bottom of my C line. And that verifies and shows that once again I get 0 or a funky voltage, which tells me that that thing is going to go and be shot. If I have got more than one fuse that is going to be blown, I'm going to be able to verify that through this as well. You know, you're going to be able to, once again, starting at the top, when we hit 230, slide it down to the bottom, I got nothing over there. Over here, I see that I'm crisscrossing that. So now I'm going to go and slide this one up to the top and slide this one down to the bottom. Once again, I'm getting nothing over there. And then I'm going to go and check across to this line over here. I see that I'm getting full value of voltage. So obviously, if I'm getting, value of voltage across the top, that's all good. But I slide down to the bottom of one of these, and it's going to have a weird value of voltage. Anything that's a weird value of voltage always indicates that the one that is on the bottom is going to go and be the bad fuse. Take a look at the 4 that are highlighted over here. If you take a look at the 4 that are on the highlighted over here, you see that every single one of them, it's got 0 volts or a bad value of voltage, and they're all going to be for the one, they're always indicating a fuse that they're touching the bottom of, the downstream side of it. Okay, that is crisscross fuse testing.